Welcome back. Apologies for the absence for a little while. I've unfortunately been rather unwell, rather busy, and also had my PhD graduation last week, so fun times. Now, after all the bait and switches in the introduction to different states of matter, it's time we settle down and look at some more exotic ones, shall we say. Before we go into non-classical states of matter, how does discussing super low temperature phases sound? My video, my decision, don't care. You can't respond in time. I mentioned helium last time around, and we'll revisit the discussion of superfluids, which occur at temperatures almost as cool as I am. Up there. Helium exhibits a superfluid state at below 2.17 Kelvin, not that far above absolute zero, where there is no energetic movement. Superfluids are cool, not just in the sense of the temperature they exist, but also in their unusual behaviour, where they move as a liquid without friction, with zero viscosity, or to put it a third way, infinite fluidity, hence the name superfluid. In the state, it can attempt to climb out of a container due to the lack of resistance it faces. And even more interestingly, from my view, its thermal conductivity within is apparently infinite, meaning it cannot have thermal gradient within the medium. It all exists at the same temperature. For example, here's a fluid in a sealed container. You can see a gradient. The heat rises, kind of thing, by convection. This doesn't happen in a superfluid, however. Everything is at the same temperature. Now, if we move on from superfluids, we have BEC, the Bose-Einstein Condensates. As the name would suggest, these were predicted by Satyendra Bose and some guy, Albert Einstein or whatever, in 1924. Just to clarify, the names are on screen with arrows. I believe they are correct. The temperature for BEC, realised, appears to be a fraction above absolute zero. And in this state, the entire medium behaves not as particles, but as one unified entity. This is quite hard to imagine, something which is colder than solid and seems to sacrifice identity for the greater power of the hive. Despite the whole colder than solid crap I quoted previously, it does kind of ring true. BECs tend to be formed cooling very low density gases right down to very, very low temperatures. Talking gases of a density around 1,000 times lower than that of air, and to a temperature of about 0.01 of a degree above absolute zero. For a fun thing to do with them, they can be used to slow the velocity of light down from 300 millimeters per second, velocity in a vacuum, to around a pokey 17 meters per second. This is a colossal slowdown, meaning that the refractive index of a BEC is pretty staggering. But I'll cover refractive indexes in the future. For a comparison here, you can see that in an atmosphere, Usain Bolt runs at approximately 10 meters per second on average to cover 100 meters in 10 seconds. In a BEC, light's still actually faster. I would hate to put Usain Bolt low running through a vacuum or in a BEC. I don't think he'd do very well there. There are other low states, temperature states of matter, such as the fermionic condensate, similar to BEC, as well as very high energy states. But I don't really understand them that much. They kind of hurt my head. So I'm going to move on to glass here, one of my favourites. So, what comes to mind when you do hear glass? Do you think windows? Most likely. Or for the alcoholics out there, pint glasses. I'm just going to carry on with the science. No judgment, you boozers. Anyway, as we saw with ice, there are different types of solids, namely crystalline and amorphous. So think of these. Crystalline, everything is well organised and regimented like a Roman legion. Amorphous, more akin to a football riot. Glass fits into the amorphous categorization of the system and is further defined by the exhibition of a glass transition when heating towards a liquid state. In a crystalline state, everything is very ordered and regimented, as like the Roman legion. The amorphous is more like the football riot because everything, they kind of know where everybody is locally, but there's no longer range formation of it. You know, whereas with a Roman legion, everybody knows where everybody else should be based on their current position. Glass can be made of numerous different materials, not merely silicon oxide and silicon dioxide, etc., mixes of our windows, but you can also get metallic alloys, ionic melts, and polymers to form them. Moving on, but keeping with the thread of polymers, we can also encounter microphase-segregated materials, which behave in an interesting manner. So we've entered an operating theatre here, and imagine you're some kind of sick, lunatic individual, much like myself, and that you've sewn a football fan to the back of a rugby fan. I'm not showing that. And then let them loose in a room where one side is discussing football and the other is discussing rugby. So the pink is football, the blue is rugby. What would they do other than bleed to death because you're a shit surgeon? If you say ask for help, no, they were in on it. If you said stand in between the halves and orient themselves so that the rugby fan can talk to other rugby fans and the football fan can talk to other rugby fans, have a cookie. And if you're asking what rugby is, doesn't matter. Get over it. Microphase-segregated materials can be formed by copolymer systems wherein you have a polymer chain that is hydrophobic, water-hating, section at one end, and hydrophilic, water-loving, section at the other end. So here you see orange as hydrophobic and blue as hydrophilic, for example. Philic meaning loving, phobic meaning hating. So, trying to think of other examples of this, say, xenophobic means a hatred of foreigners, for example, or arachnophobic means a hatred of spiders. I'm not advocating either of these things, but if you're going to hate something, hate spiders, I guess. Philic, francophilic, people who love French people. There you go. That's one word I can think of. So we've got a very, very simplified view here, making it look like eraser when you've got the two different coloured ends, just to simplify everything. Now imagine when you expose this to different solvents. If you're going to expose it to a mixture of water and oil tends to float on water. I've presented it sideways here. The orange bits will stick into the oil, the blue bits will stick into the water. But what if it's not a 50-50? And what if you've taken a few drops of oil, shaken it up? Well, you can get formations of spheres with the hydrophobic ends encapsulating the oil within them and keeping it safe from the water. So in this situation, solvent is water, but if you've got an oily environment in the middle, or even if you don't, for that matter, the hydrophobic ends will tend to stick together and hide away from the water as much as possible, forming spheres. Imagine this in a three-dimensional shape. And you can call these micelles. They can be used in a variety of different things, though, including in detergents, as well as in drug therapies these days to introduce things which wouldn't normally be capable of going into the bloodstream. This is actually quite an interesting area of research, which I've had a mixed amount of exposure to in the line of work I've had. We'll come on to that, though, hopefully in the next few episodes. So, moving on, looking at magnets. The last of the miscellaneous phases I'm going to cover talks a lot about magnets. Magnetic materials, Insane Clown Posse, I am going to actually explain how it works. So we're going to look at a few elements here, some good examples in the transition metal area. So we've got iron, copper, tungsten, and other ones in that kind of area. The electrons in them can sit unpaired, unused in bonding, and probably unloved. In some bulk solid, magnetic moments on different atoms are ordered, and this can give rise to ferro, antiferro, and ferrimagnets. So, for the first of these, we are going to look at ferromagnets, taking iron as an example because that's literally where ferro comes from. Ferrous, iron, Fe on the periodic table. In the ferromagnet, shown here as a very, very simple example, all the magnetic moments within it are aligned in one direction. This is the easiest one to think of. They are all the same size, all pointing the same way within a domain. And if they're all aligned with each other like that, we get a permanent magnet. Of course, you can actually break permanent magnets by increasing the temperature on them massively or smacking them really hard with a hammer, for example. I've actually done experiments on that when I was at school. It's quite fun. We tried making permanent magnets and then demagnetizing them. It was all right. Got to hit things with a hammer. The temperature known for breaking down the magnetism is known as the Curie temperature, or the Curie point. So if you want to stop sticking things to your fridge or to everything like that, just heat up, say, iron to 768 centigrade, around about 1040 Kelvin. Magnetization breaks down. So we move on to the opposite, antiferromagnets. So rather than being an evil twin, these have two networks comprised of equal magnitude but opposite directions. As you can see, the orange arrows are pointing at each other. These balance out, cancel out. A good example of this, though, would be nickel oxide, wherein half the nickel atoms are directed one way, the other half were directed the other way. Ferrimagnets, they're a little bit weirder. We again have two different directions, but two different magnitudes. So if one lot are pointing one way, the big ones are pointing to the right and the little ones are pointing to the left, we have a net magnetism going in the right-hand direction from north to south. It's because you get two different oxidation states of the metal within it. So imagine in the case of magnetite and iron oxide. Iron can exist in two oxidation states. Now we'll go more into depth on oxidation states in a future episode, but believe that it can have two different oxidation states of 2 and 3, or +2 and +3 within magnetite. These different oxidation states have different magnetic moments, and therefore if they don't balance out because of the different moments, you get a bulk magnetism, which isn't quite as strong as for the ferromagnets because you have opposition in them, but it is there, unlike in the ferromagnets. So we're going to leave it there, but next time I will be back and starting to look at my favourites. You've sat through the miscellaneous phases. You've sat through the standard phases. Next time, liquid crystals, people. That's what I have my PhD in, and I'll hopefully not bore you quite as much as with these ones and not sound like quite as much of a weirdo. Anyway, I've been Alan Robert. You have been far too patient with me. Thank you very much, you awesome people. I thank you endlessly for watching. Ciao, my friends.